Welcome to qnawire.
Hey everyone, this is question number 82 from chapter 14. In this problem, we're told that a nurse wants to cool down a soft drink, which is mostly water. We're given the volume of the water, 2 liters. She pours it into an aluminum mug. We're given the mass. And then she adds 0.12 kilograms of ice at minus 15 degrees Celsius. We're told that the mug and the water start at 20 degrees Celsius. And we're asked to find the final temperature of the system. This kind of problem should be looking pretty familiar by now. But it's another one of these problems where we have a system made up of multiple parts that Q has to be calculated for. So our two Q's are Q equals MC delta T, and then if we have a phase change, we have Q equals ML, F, or V. And we're told in the problem that we have no heat loss, so we're going to end up setting the 3 Q's of the system equal to 0. So we can go ahead and start solving for Q's. So Q of W equals, water is not changing phase, so it's just going to be MC delta T. So we have 2 liters of water. We know that 1 liter is equal to 1 kilogram in mass, so that's 2 kilograms. C for water, 4.19 times 10 to the third joules per kilogram K, and then times our delta T. We don't know our final, so that's going to be a big T that all 3 are going to have in common, minus 20 degrees Celsius. And if you plug that in and solve, you get an expression. You get 8,380 joules per K times T minus 1.676 times 10 to the 5th joules. So now we can go on. That's water. We can do the mug now. So QM equals, no phase change, so just MC delta T, M 0.257 kilograms. C for aluminum, 910 joules per kilogram K. And then T, again, we don't know our final, but our initial 20 degrees C. And if you plug that in, you get Q mug is equal to 234 joules per K times T minus 4.68 times 10 to the third joules. So now we go on to ice. Q ice is equal to, this one gets a little more complicated because we have the change in ice because it's at minus 15 degrees Celsius. So we have to get from minus 15 to 0, and then we have to melt at 0, and then we have to get to our final temperature, which is above 0. So we have three parts. We have M ice, C ice, delta T, and that's going to be our change to 0 degrees. And then we have mass of the ice and heat of fusion because it's melting. And then we have mass of the ice, but now our C is water because it's melted and is now water, and then delta T to our final. So QI equals 0.12 kilograms. C of ice is 2010 joules per kilogram K. And our change is 15 degrees Celsius, 0 minus negative 15. And then we have plus our L of F. This can be in parentheses and pulled out to the front, or excuse me, brackets and pulled out to the front because our mass, as you see, is the same mass of ice. That's not going to change. So then that becomes bracketed as well. So now we have plus just L of F, 3.34 times 10 to the 5th joules per kilogram. And then we have plus M's pulled out, C for water, 4.19 times 10 to the 3rd joules per kilogram K, times change in temperature T, that's our final that we're looking for, minus 0. That's what it melted at. Okay, so if you very carefully simplify that, close that bracket, you get Qi is equal to 4.37 times 10 to the 4th joules plus 503 joules per Kelvin times T. So now we have our 3. We talked earlier that our sigma is going to be equal to 0. So now we just set all this equal to 0 and solve for our final temperature. So we have T equals 0 equals 8,380 joules per K times T minus 1.676 times 10 to the 5th joules plus 234 joules per Kelvin T minus 4.68 times 10 to the 3rd joules plus 4.37 times 10 to the 4 joules plus 503 joules per Kelvin T. Okay, and when you combine like terms and solve for T, you get T equals 1.286 times 10 to the 5th joules over 9,117 joules per K. Joules cancel, left with Kelvin, and we get 14.1 degrees Celsius. And notice this as our final temperature, 14.1 degrees Celsius. We assumed when we solved this problem that all the ice melted, and we are correct because 14 is much above the freezing point of ice, which is 0 degrees Celsius.